Welcome back. In this video, we're going to start talking about electricity, starting at the physical level, at the nature. Nature, all of that exists is electrical charge, and the electrical charge is what carries the electricity from charge is the one that carries electrical values or charge. In different materials or in the air or whatever. And our understanding of charge and our ability as engineers and computer scientists to take that and put it to use has enabled humanity to do all kinds of stuff that if you lived a few hundred years ago, it would all look like magic. From keeping your food cold in the refrigerator, to cooking your food in the stove, to driving your car, to being able to have a cell phone and a computer, being able to know where you are in the world using the GPS information, to being able to sense all kinds of stuff, the medical equipment we have. Pretty much there is very little in the world that does not benefit from humanity's understanding of charge and engineers' ability to take charge and put it to use for what we want to do. So we're going to start by talking about charge, what it is, so you have a sense of that. For most of the time, we abstract charge properties in the form of a current and voltage, which makes it easier for us to use those ideas to implement devices that would be useful to us. And understand how they behave, being able to model what they do. So that's how we're going to go. We're going to start with the charge, then we're going to describe what the current is in relation to charge, voltage in relation to charge, and then Ohm's law, which is a critical law in electrical circuits, a fundamental law. We'll introduce that and have a conversation with it about it. Now remember, charge is the only thing that is a real physical, honest to goodness thing that is there in the nature. We didn't create it, we just learned how to take advantage of what actually exists in the nature. Okay, having said that, let's jump in and put some of these things in forms that we can actually use to design with, analyze circuits and things of that nature. All right. So let me close this. Okay, so let's start with current. Let's start with charge. So electrical charge is not the only kind of charge. There are other charges. They're like, for example, there's a magnetic charge, there's a color charge, and those are fine. Our focus here is on electrical charge. And what it is basically in subatomic, if you have an atom, yeah, right? And if you look at an atom, let's go ahead and draw a little simple model of an atom. And if you have never had it, it's not a big deal. It doesn't prevent you from working on this. So at the nuclei of a thing, we have a neutron and we have proton. And the protons have a positive charge associated with it. And this is in the nuclei, okay? And nuclei is very dense, very heavy. So think about a core, a center that it does. And around these, there are these electrons that are floating around in a circular fashion. And just to give you kind of a magnitude, this is not precise, but to give you a magnitude, if the center was a basketball, for let's say, and neutron or proton was sitting in the basketball, and that was the size of an actual basketball, then the electrons will be circling around within a mile of that basketball. Basically, what I'm saying is that these guys also have almost no weight compared to the neutron and proton, have no weight. So and these guys are floating around. These electrons, each one of these electrons, and there could be 1, 2, 3, 4, 5, and they could be in different orbits. These are called covalence energy or energy levels. So you can have electrons running around all over the place. You could have 1 electron, 2, 3, 10, whatever, depending on the material you have. So atoms, I forgot to say, atoms are basically the smallest part of a element that has the properties of that element. And then electrons have a negative charge, protons have a positive charge. And so that's basically it. And what we are we are interested in these electrons, whether they are there or not there. We use them today for electricity. We use them, we kick them up and down. And every time we change their energy level, we get light. And those are like LED lights you guys have heard of, comes from there. We're not going to spend a ton of time on electron. I just wanted you to know kind of what an electron is, what an atom is, what's a neutron, what's a proton, and things like that. But we're not going to spend, that's more of a physics class, and we're going to, you either going to take physics, you're probably going to take physics in the future, and you get into those in much more detail, and also chemistry. If you take chemistry, you'll get into those as well. So what we're going to do, we're just going to say, if you take that many electrons and collect all the charges, we're going to call that a coulomb. So the unit for charge is coulomb, and 1 coulomb, and it's represented by a C. So 1 coulomb is equal to having 6.24 times 10 to the 18 electrons, charge equal to charges of that electron. So that's what we call. So Q, we usually use Q to represent charge, and is 1 electron. So far, so that was kind of more or less just kind of a general interest. That's kind of cool to talk about, but it's mostly physics. We are here to talk about electrical circuits design. We want to use that information. So we need to know what a charge is, but we don't spend a lot of time on it. We pretty much in electrical engineering using current and voltage to make models and design circuits and build circuit. And what is current? Current is basically like rate of flow, speed of flow, or flow rate for electrons. So how much electron passes a certain point in 1 second. And the equation we use to do that, delta, is a fancy way of saying, so the symbol, the Greek symbol, the triangle, is called delta. It's capital letter delta. And this basically is the shorthand for saying change in charge. So if you take change in charge divided by change in time, right? Change in time, that would be your current. So current is simply flow rate for charge flow rate, or speed of charge moving. Okay, so that's great. And then voltage is the other one, and then the units are in ampere, and the letter we use to indicate amp is an A. I, most of the time, I is used to refer to current. So if you see I in electrical engineering, that's talking about current. V is the other parameter we look at. The V is voltage, and the unit for voltage is volts. And V, capital letter V, we used to refer to voltage. And that's, again, now that we know what delta is, this basically is saying it's a change in energy over change in charge. Okay, so that's what it is. Now, if you have, I wrote this as if you never had calculus. So the rate of delta, we know change. We take the one value, subtract the other value, that becomes a change. Now, if you're taking calculus, a lot of the time we write it as derivative of E with respect to Q, and derivative of Q with respect to time. And for all practical purposes, we are okay to use this form for now. But as you get more sophisticated and we move down, we'll start using the derivative instead of saying change. It's more precise. And we are able to work on things that are not linear, not a line, but they're curves or doing other things. Okay, so that's the current and the voltage. Now we know what they are, we know what the units are, and all that. Okay. All right, so that's so now, okay, so now we know there are a lot of times people take water, and in order to try to understand what electricity is, they try to use water to do an equivalent. So that's fine. In electricity, we have, for example, when we talk about voltage in electricity, we typically compare 2 points, point here and point here, And we typically say if this is plus and this is minus, this is 5 volts. That would be the difference from here to here is 5 volts. If it was a water and I had some water up here, right, and there was a pipe that went to the water in a lower space, let's say this is at the height of 10 feet, and this is at the height of 0. So there's a potential energy. If I open this hole in here and put a hose between, the water will flow this way. This is the same way as here. If I put a wire between this, you will have the electricity flow through it. Okay. And then the rate at which this water flow in the pipe is called current. In the electricity flows, electrons flow in the wire. That's the same thing. That was basically we call the I. This we call the V. And charge is the amount of water. This is Q. So how many molecules of water, how many grams of water, whatever you have there, that would be the charge. That's kind of the basic thing you're measuring. Okay. And resistance. Resistors, or resistance in a wire, we typically refer to it with an R. And a resistor, basically all it is how hard is it for an electron to move through it, through the wire. An analogy for water would be, let's say you've got a water hose, and you pinch the middle of it, so water has to push through your point of pinch. And so what you're doing by pinching the wire, you're making it harder for water to move through it, so less water will move through it. That same thing happens here. And that kind of, so resistance is R, charge is Q, or capital Q, doesn't matter for now. And then capital I for current, capital I for V for that. We usually use capital values if the values are constant. If they're changing, then we use small letter. But for now, everything we do, we use capital letters. Okay. So at this point now, what we've got going is we have an analogy. That analogy is pretty good for this class, but as if you move down to higher and higher level and start removing some of the assumptions we have here, that what an analogy, just excuse the pun, but doesn't hold water. It kind of loses its effectiveness as we move down the path. Okay. All right. So now that we know current and voltage, Simon Ohm lived a few hundred years ago, and he observed the relationship between current and voltage and called that relationship resistance. So if you go back to what Ohm's law strictly is, or the way he stated it, he wrote it this way: that R, the resistance, is a ratio of voltage to current. Okay, and typically if current is in amps, voltage is in volt, then R would be in ohm, and typically we use a omega, a Greek letter omega, for units ohms. Ohms is the units for resistance. Now, doing a little simple algebra with it, you can take the R and I and exchange their position, and you'll end up with this equation. So these two equations are identical. So this is a valid Ohm's law equation too. Another way to write it, if you multiply both sides by R, you'll get this equation, which is another way of saying Ohm's law. So these are the three valid way of writing Ohm's law equation. And the way you use them is pretty straightforward. If you have a resistor and somebody gives you a volt, for example, in here, if somebody tells me this is 5 volts, we haven't really talked about it, but this is a voltage source. Its job is to give you 5 volts. If I have a 5 volts, that means from here to here is 5 volts. If that's 5 volts and I know this is 20 ohm, if I want the current, I apply the Ohm's law. I equals to V over R. V is equal to 5. This is 20, so that becomes 0.25 amp. And since we know the engineering notation, we haven't got to it. When we get to it, so sometimes we write it in engineering notation since we like whole numbers, but that's okay. We can leave it like this for now. Okay. So that's Ohm's law, pretty straightforward. You typically in this equation, you have 2 of these values and you find the third one. So that's pretty much it. And by the way, if I forgot to say, this is a symbol for a voltage source, and you see that pretty often. This side, that this is saying is that this point is higher than this point by 5 volts, and this is how we write it. So that's as far as the Ohm's law is concerned, that's pretty much it. We're going to use that Ohm's law plays a really important role in our work. Current and voltage also play a pretty important role. Later on, we're not going to talk much about charge after this point, but it's important to know what the voltage and current really are measuring. In reality, they're measuring electrons, the number of charge carrying electrons in your circuit. All right, so this is a numbering system. The engineers have their own notation, which is kind of a variation on scientific notation, but it's very specific for engineers. The big difference is that we only look at 10 to the power of multiples of 3. So why do we do that? We don't, so for example, if I need to write this, it's really difficult for me to write all these 0. If you miss a 0, it's very difficult. So what we do, instead of doing that, we'll basically write it at 25 divided by 10 to the 6, or multiply by 10 to the minus 6, which is the same thing. And what that does, actually, I see an error in here. This should be 250 times 10 to the minus 6. Okay. So there should be 250 times 10 to the minus 6, so it would be 250 microamps, which is great. And so instead of having to write 00025, I use these notations here to write it and give it a prefix that tells the world that is the 10 to the power of 6 that I am not writing. So what we have, these are the most common ones we use. I don't know if we're going to end up using any of these 3, but I put it there for completeness. But if you're talking about in computer and electrical engineering, you most likely have things that are 10 to the power of 15, 10 to the power of 12 tera, 10 to the power of 9 is called giga, 10 to the power of 6 mega, and kilo. And over here, most likely we use milli, micro, nano, and pico. I don't think you're gonna see these very often, but it's good to know. And I don't think you're going to see these very often, but you will see milli, which is 10 to the minus 3, or another way to write it is 1/1000, or 10 to the minus 6 is 1/1,000,000, 10 to the minus 9 is 1/1,000,000,000, and things like that. Okay, so it's good to know these, because instead of having to write 0.000 that, or write 250/1,000,000, it's a lot easier to just write 250 microamp and be done with it. Okay, and chess of errors, that is easier for communication. So the power of tens in engineering notation is something you need to know, at least the one that is commonly used, like these 2 groups. If you don't want to learn the rest, that's fine for now. Okay, so that pretty much brings us to the end of this video, which all it was trying to get us to think about charge, current, voltage, and Ohm's law. Take care and see you on the next video.